Hello and welcome to the second video of the FP1 chapter Complex Numbers. As usual, on the screen, two starter questions for you. Give these a go if you've got time. The first one reviews the previous video and the second one reviews an idea from GCSE that we are going to use in this video. So the first one, solving this using the quadratic formula, we have minus 5 plus or minus square root of 5 squared minus 4 times 2 times 6, all divided by 2 times 2, which is 4. And that should give you the final answer, minus 5 plus or minus square root of 23i divided by 4. Two complex roots. Second, rationalizing the denominator. I hope that you remember this from your GCSE work. We multiply top and bottom by something very similar to the denominator, but different enough that we know it will produce a non-surd or rational number in the denominator. And that's because when you do 6 times root 5 and 6 times minus root 5, they cancel out. And you end up with 6 squared minus the square root of 5 squared, which is just 5. And on the top you get whatever the consequence is. Here we have 42 plus 7 root 5. So our rationalized number, and then simplified, is this. And we'll use an idea very, very similar to that later in the video. So our quick overview. In this video we are going to multiply complex numbers, which is quite easy, it's very short, which is why I've put two together, and then talk about something called complex conjugates, which will help us to divide complex numbers, among other things. To multiply two complex numbers, it's very easy. We've already done the precursor to this, which is to multiply by a real number. We just expand the brackets as normal. The idea we've been using so far is that the square root of minus 1 is I. In this case, we are going to use the reciprocal, that I squared is equal to minus 1. So this is really the only new thing. If we have z1 and z2 and we want to multiply them together, we put the brackets together as usual, and then go ahead and expand. 2 times a 3 is a 6, then we'll have plus 21i minus 8i, and then we'll have a minus 28i squared. And of course we should put the two I terms together, but more importantly is not to leave the I squared as an I squared term, but change that I squared into a minus 1, which makes this a real term which can be added to the 6. So we have, if I make it really clear, 13i there, and then minus 28 times minus 1 from the I squared gives us a plus 28, and our final result is 34 plus 13i. And this is the result of z1 times z2. It's as simple as that. So a few examples before we move on to the complex conjugates. Here we go, doing pretty much the same thing. We've got 8 plus 12i plus 10i plus 15i squared, which we will change into a minus 15, 8 minus 15, minus 7, and a 22i. The next one, don't be tempted to square both of those directly, as I've seen some students do. Write out the brackets. 49 minus 2 lots of 7 times 4i plus 16i squared, and again that will turn into a minus 16 because of the I squared. So we've got 49 minus 16, which gives us 33, and minus 28 minus 28 minus 56i. Now these next ones are very useful, because you should never leave a power of an I by itself as a power. You should simplify it. An I cubed is just the same as I times I squared. And I squared we can turn into minus 1, so this is equivalent to minus I. In the same way, I to the power 4 is like I squared times I squared, which is minus 1 times minus 1, which gives us 1. So I to the power 4 is just a weird way of writing 1. Here we've got 2i all to the power 5, so the power 5 applies to the 2, and also to the I. That gives us 32 as the number, and then I to the power 5, if I do this just down below for a second, is I to the power 4 times I, and we know I to the power 4 is 1, so this actually simplifies down to I. And then I hope you can see a cyclic element here. If you've got I, obviously that's just I. I squared is minus 1, I cubed is minus I power 4 is 1, I power 5 brings you back to I, and as you go to I power 6, that's the same as I squared, I power 7 is the same as I cubed, and so on. Now we can talk about complex conjugates. Now remember, for a complex number defined in terms of the real numbers a and b, we can write it like this. And it's very important that you understand a complex conjugate is related to a complex number. So whatever fixed number this is, it has a complex conjugate associated with it. If you change the number, the complex conjugate changes. They're a pair. So if you have z equals a plus bi, then the complex conjugate is defined in terms of those same a and b, and we write it as z star to show that connection. It's very easy. You just change the sign here. Plus to a minus. Obviously, if this is a minus, then the negation changes that back to a plus. So z and z star are a pair. They use the same a value, the same real value, the same b value, except one is a positive and the other is a negative. And it's as simple as that, but it's a very useful thing to be able to do. So a few very quick examples here. Given that z is equal to 4 minus 3i, write down z star. Now that's very easy. It is as simple as 4 plus 3i. Z plus z star, so we've got 4 minus 3i plus z star, which we just found out is 4 plus 3i. Of course, the minus 3i and the plus 3i cancel, and that gives us 8. And it's quite useful sometimes to be able to get a real number out of a complex addition. In the same sort of way, we've got 4 minus 3i minus 4 plus 3i. And that gives us a cancelling of the 4 and the minus 4, and minus 3i is minus 6i. So here we've got an imaginary number from subtracting two complex numbers. Lastly, if we multiply the two together, 4 minus 3i times 4 plus 3i, you can see, I hope, that the minus 12i plus 12i will cancel, and we'll have 16 minus 9i squared. And as before, the I squared there is a minus 1. That becomes 16 plus 9, which is 25. And again, same as part B, it can be very useful to know that a complex number multiplied by its own conjugate will give you a real answer. To make clear how useful that is, I'm going to do the same questions with the general complex number a plus bi. And I hope that you can follow through the ideas that z star here, we've already got a minus bi. Here we're going to find a real number, because if you're adding its own conjugate, you will always have the imaginary parts cancel out, and you will always have 2 times the real part as your answer. That can be very useful. In the same way here, you will always have the real parts cancelling, and the imaginary parts will combine. So here we've got 2bi. Z times its own conjugate. As before, this times this will cancel with this times this. And you'll have a squared minus b squared I. Sorry, I squared. That's very important, because the I squared will always turn into a minus 1, so this will always become the real part squared plus the imaginary part squared, but without the I, so it will be a real answer. And that's key for the next thing we're going to look at, because we can use these to help us to divide complex numbers, manipulating them very similar sort of way as we did to rationalize. Now here we're going to need two different numbers. So I've called the first one Z and the second one W. And each of these has its associated complex conjugate. Z has a Z star and W has a W star. Now in order to divide these two numbers, what we want as a final answer is a complex number in the usual form, a real part plus an imaginary part. We don't want to have a fraction left in there. So what we're going to do is take an idea from our rationalizing of the denominator, and what we said on the previous screen, that a complex number multiplied by its own conjugate will always give us a real number, and we're going to multiply top and bottom by the conjugate of the denominator, c minus di. And the reason we're going to do that is because we know from what we just saw on the previous screen that the denominator here will give us a real answer. So we're going to have something fairly complicated on the top. We've got AC plus CBI minus ADI minus BDI squared, and I won't bother simplifying that for now, but if you had numbers obviously you would. And on the bottom we're going to have C squared plus CDI minus CDI, which will cancel, that's the whole point. And then we're going to have minus D squared I squared, which will become plus D squared without the I. So you'll simplify the top bit, you'll have a real part and an imaginary part, and then you'll have a real number on the bottom where you can divide your two parts, real and imaginary, on the top by that real number and have it in a form like this. Now I've done the algebra there to show that it will always work because of this, but it's not easy to see how it's going to end up until we get into the numbers. So let's have a look at some examples. Write this in the form a plus bi. So we're going to do exactly what we had on the previous screen. We're going to multiply by the complex conjugate of the thing in the denominator. And on the top, we've got some numbers now. 10 plus 8i plus 15i plus 12i squared, which will be minus 12. On the bottom, we've got 2 times 2, 4, minus 6i plus 6i, which cancel, and then minus 9i squared, which becomes plus 9. And I've spoken through it there, but I haven't written everything that I said. The more you do this, the quicker you'll be able to jump to this line. So then, of course, we've got a minus 2 on the top, and a 23i, and then we've got a 13 on the bottom. Now that's not a very nice number, but if we really want it in the form a plus bi, we can split that into two fractions. So long as they are real numbers, this is in this form. And that's everything you need to know in order to be able to do practice questions from exercise 1C about multiplying complex numbers, and 1D about complex conjugates and dividing complex numbers. And maybe I'll see you in the next video.